Magnetic Random Access Memory (MRAM). MRAM stands for Magnetoresistive Random Access Memory and is a non-volatile type of RAM. Magnetic state refers to the electrical resistance of a metal when it is placed in a magnetic field. The MRAM uses magnetic states and magnetization direction in a ferromagnetic material, a material which is highly susceptible to magnetization to store data bits, for storing data, and magnetoresistance for reading the stored data instead of using the electrical bits to store your data. Information is stored using electron spin. It is sometimes called as ideal memory. As it is a non-volatile type of memory, no refresh is required to retain the data and the power consumption is very less. MRAM, Magnetoresistive Random Access Memory, is a method of storing data bits using magnetic states instead of the electrical charges used by devices such as Dynamic Random Access Memory, DRAM. By combining the high speed of static random access memory, SRAM, and the high density of DRAM, MRAM promises to significantly improve electronic products by storing greater amounts of data, enabling faster data access and consuming less energy than existing electronic memory. MRAM got its start in 1984 when Dr. Arthur Pohm and Dr. Jim Doughton were both working for Honeywell. The scientists conceived a new class of non-volatile magnetoresistance memory devices that offered random access and high density. In 1989, Doughton left Honeywell to form his own company, Non-Volatile Electronics Incorporated. He also entered into an agreement with Honeywell to sublicense the MRAM technology. MRAM got a big boost in 1995 when the U.S. Defense Advanced Research Projects Agency, DARPA, provided funding to 3 private consortia researching the viability of making MRAM a general-purpose memory with high density, high speed, and low power usage. The consortia were led by IBM, Motorola, and Honeywell. Working principle: MRAM uses MTJ, magnetic tunnel junction, to store bits of data. MTJ comprises of 2 layers of ferromagnetic materials, the reference layer and the free layer. An insulation layer is used to separate these two. Storing of a logical element, 0 or 1, takes place by changing the resistance of an MTJ. The resistance depends on the relative spin orientations of 2 ferromagnetic layers and can be of 2 types, high resistance or low resistance. The reference layer is used to maintain the magnetic direction, while the free layer can have its direction changed by using magnetic fields or by applying polarized currents. A logical 0 is stored when both layers have same direction, hence MTJ has a low resistance. A logical 1 is stored when both layers have different direction, hence MTJ has a high resistance. Why MRAM should be used? DRAM has the advantage of being cheap, but is comparatively slow and data is lost when power is off. SRAM, on the other hand, is faster than DRAM. But it can cost up to 4 times as much as DRAM, and data is lost when power is turned off. Flash memory saves data when the power is off, but the process is too slow and consumes a lot of power. MRAM potentially combines the density of DRAM and the high speed of SRAM and the non-volatility of flash memory or hard disk, and all this is done using very less power. MRAM can resist high ionizing radiation, can operate in extreme temperature conditions, and thus is very suitable for aerospace applications when combined with suitable CMOS technology. Advantages of MRAM. MRAM offers several advantages over traditional memory technologies like DRAM and SRAM. Firstly, MRAM is non-volatile, which means it does not require power to retain stored data. This feature makes it ideal for use in portable devices that require long battery life. Secondly, MRAM is extremely fast, with read and write speeds that are comparable to DRAM and SRAM. This feature makes it ideal for use in high-speed memory applications like cache memory. Finally, MRAM is highly durable, with the ability to withstand extreme temperatures, radiation, and physical shock. This makes it ideal for use in harsh environments like outer space and military applications. Potential applications of MRAM. MRAM has the potential to revolutionize the way we store and access data, with several potential applications in various industries. One of the most promising applications is in portable devices like smartphones and tablets, where MRAM's non-volatile nature and fast read and write speeds can significantly improve battery life and performance. MRAM can also be used in cache memory applications, where its fast read and write speeds can significantly improve computer performance. Another potential application of MRAM is in automotive electronics, where its high durability and ability to withstand extreme temperatures can significantly improve reliability and performance. MRAM can also be used in military applications, where its high durability and ability to withstand radiation and physical shock make it ideal for use in harsh environments. Applications of MRAM. MRAM has a potential in all memory applications in these devices. Digital cameras, cellular phones, MP3, HD TV, laptops. What is MRAM used for? MRAM has been around for many years, but its adoption has been slow, in part because of manufacturing challenges, but also because the chips hold relatively little data, making them suited to only specific use cases. Even so, MRAM has been making steady inroads into a number of industries. Aerospace, defense, automotive, robotics, consumer electronics, medical devices, Internet of Things, edge computing, industrial operations and automation, energy management and automation, storage controllers and cache, artificial intelligence and machine learning. MRAM can help address the challenges of other memory technologies. It has the potential to replace both DRAM and SRAM, and it beats out NAND flash in terms of performance and durability. MRAM also consumes a relatively low level of power, and it's resistant to radiation. As a result, MRAM could potentially benefit a number of use cases such as auto powertrain systems, aircraft black boxes, or medical devices such as ventilators or RFID tags. Despite these benefits, MRAM is still an emerging technology, and it will be several years before its full potential is realized. For this reason, it's made greater gains in some industries than others, where it is still in the early development stages. But there is a good deal of interest in MRAM right now, and many companies see the technology as promising enough to warrant further research, development and investment. Magnetic Random Access Memory, MRAM, is a promising technology that has the potential to revolutionize the way we store and access data. With its non-volatile nature, fast read and write speeds, and high durability, MRAM can significantly improve the performance and reliability of various electronic devices.